This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is ocean thermal energy. The ocean thermal energy conversion idea is an old one. The idea is to use the delta T in the ocean for a power cycle for sustainable energy. So imagine we're in the tropics and the surface water is 85 degrees. Nearby there's much cooler water, 300 feet straight down. That water might be 50 degrees. This is sufficient temperature change that with the right working fluid, ammonia in this case, we could get a system to produce a heat engine. And we're going to look for the Carnot efficiency. We're going to look for the water flow rate for a 10 megawatt power cycle. This would be enough to power, say, 7,900 average US homes. And then we're going to look for the pipe diameter for a velocity of 1 meters per second. We want to have it slow enough so that fish can escape. We want to capture water, not fish. All right, Carnot efficiency is defined as 1 minus the cold temperature divided by the hot temperature. We can compute that. The cold temperature is 50 Fahrenheit. But now we need to convert this to absolute. So I'm going to add 460 and that'll give me Rankine. Dividing by the hot temperature is 85 plus 460 to convert to Rankine. And this value is 0.0642 or 6.42%. That's a very low efficiency. All right, what's the heat rate? What's the water flow rate for a power cycle of a certain size? Well, the relationship between heat rate and mass flow rate of water through a heat exchanger is Q equals m dot Cp delta T. This would be from a heat exchanger. So we could solve that for m dot. M dot would be QH, Q dot H, divided by Cp delta T. Let's use Cp value of 4180 joules per kilogram per Kelvin, but we need also the Q dot term. Well, Q dot is going to come from looking back at the efficiency definition. The efficiency for a power cycle is the power divided by the high temperature heat rate. If we're going to use power, it works out that way. So I could solve for Q dot H. Q dot H is going to be the power divided by the efficiency. So it's not a very efficient machine, so we need a lot of heat. The power is 10 times 10 to the 6th watts, that's 10 megawatts, divided by 0.0642, so that pushes the heat way up, 1.557 times 10 to the 8th watts. Very large number. And now we can combine that with this relationship here to get the mass flow of the water. M dot for the water is going to be this large heat rate, 1.557 times 10 to the 8th watts, divided by my specific heat, 4180 joules per kilogram per Kelvin. And then my temperature difference, I'm going to use 85 minus 50 Fahrenheit. But let's fix that. Up here I'm going to say I've got 1.8 degrees Fahrenheit per 1 degree Kelvin. So that'll do my conversion there. So the kelvins will drop out. When I compute this, I get 1916 kilograms per second. That's a big number. That's almost 2 metric tons. You have to move a lot of water to get the heat to run a low efficiency system. All right, the pipe size is hidden in here. I'm going to use, that takes care of part B. The pipe size, mass flow rate of water is equal to density times area times velocity. That the pipe is hidden in there. Let's find the area as m dot divided by density divided by velocity. I've got my mass flow rate is 1916 kilograms per second. My density, let's take 1030 kilograms per meter cubed. That's for seawater. Seawater is a little more dense than pure water. My velocity was 1 meters per second. When I compute that, I got an area of 1.86 meters squared. I'm almost done. I need to use the idea that area is pi times d squared over 4. So I could solve for d as the square root of a times 4 over pi. And if you put 1.86 meters squared in there and compute that, you get the d is going to be 1.54 meters in diameter. That's a pretty big tube. Many of us could stand up in a tube that size. Sorry, I'm not much of an artist. Big pipe. Everything about this is big. Some couple issues with ocean thermal energy conversion. One is that seawater is corrosive. So there might be some material issues here. Certainly, you have to choose the right materials that might add to the expense. The mass flow is large. The heat exchangers are going to be large. Everything's going to be large. Well, the capital cost is going to be large. It might not be prohibitive, but it's not going to be cheap. And then finally, this is a tropical location in the tropics. We've got sea life in the pipes. What happens is the nice velocity, like 1 meters per second, things like coral and barnacles are going to settle in there and say, oh, this is a free lunch. The water comes by and brings them food. So you're going to have scheduled cleaning to deal with the biofouling, I think they would call it, biofouling. All right, let's recap. We've got an ocean thermal system where it's sustainable energy because the heat comes from water, which is just sitting there. We can pump it. The efficiency is low, however, because the temperatures are close together. Those temperatures aren't very far apart. Low efficiency means we've got to pump a lot of water, and we'd have to steal some of the energy we're producing from the system to run these very large water pumps. So there's no free lunch there. And then if you remember that in any engineering project, biology is going to have an impact, then all will be well.